All right, I am ready to get started, so we will jump into that. Just gotta find my controller. All right, cool. So I'm Drew Wissenat. I am a mentor for Team 538. I am on the Regional Planning Committee for First in Alabama, and I'm a control system advisor at the regionals I go to. So if you go to Huntsville, you'll see me there. And if you go wherever else ARAB goes, if they go anywhere else, you'll see me there too. I'm recording this, so this will be put on YouTube later for you guys, our guys, and then any other people who want to see it. So I'm here to talk to you about the control system. So the control system is just a bunch of parts. They're very special parts for the robot. They're in kind of three groups: sensors, actuators, and other. You can think about the control system kind of like being the nervous system of the robot. The actuators are just barely in the control system. So does anybody know what I mean when I say sensors and actuators? Does anybody not know what I mean when I say that? Okay, good, good. All right, so a sensor is anything that tells you information. I'm going to use myself as an example here because I have a sensor. Got one right here in my arm. This is a sensor to detect my blood glucose because I'm a type 1 diabetic. Now, your body has built-in sensors to tell you if your blood sugar is high or low. The problem is, mine has that too, but then my body doesn't do anything about it. My body doesn't have a functioning actuator to do something about that information. Your body does if you're not diabetic. So if your body detects you have low blood sugar, what does it do? You might know. Or if it has high blood sugar, let's say that. Starts with an I. Insulin. Your pancreas sends insulin to your bloodstream. Now, my body can't tell me that my sugar is high or low, so I have a reader to read the number. So it's a little high right now, but it's not too high. The control system is kind of like that for the robot. It has sensors and then actuators. So a sensor gives you information or detects information. An actuator does something. So for those coming from Lego League, what's an example of a sensor you guys might have used last year?
Touch sensor.
Touch sensor. What else?
Color sensor.
Color sensor. What's a giveaway that those are sensors? The word sensor. All right, but what about a gyroscope? That's a sensor. It's not called a sensor, but it is a sensor. All right, now an actuator does something. What's an actuator that you had on your robot? Motor. A motor is a very common actuator. If you look at this frame of a robot right here, there's 4 motors on it. So the actuators aren't strictly part of the control system, but they kind of are. It's weird. So your control system is what lets you control the robot. Now, when I talk about the different devices today, I'm going to call them smart and dumb. So the control system has smart devices, and the control system has dumb devices. Motors are dumb devices. And we'll see what that means in a few minutes. Any questions so far? Everybody clear on what we're talking about today? All right. So the control system is something you need to control the robot, otherwise it won't work. This is probably the most expensive, most important part of the control system. It is called the RoboRIA. Now, if you're coming from Lego League, your control system was basically the brick, and everything plugged into the brick. Not so with FRC. This does some of the job of the brick. I'm going to pass it around. You guys just go clockwise around the room with it. The RoboRIA is made by National Instruments. It's the main controller. If you'll notice, there's a bunch of different kinds of ports on it. I'm going to talk about what some of these ports are. And you can program it. And FRC first officially supports using LabVIEW, which is a visual block-based language, C++ and Java. And a lot of teams use Python. It's not officially supported, so if you have a problem, FIRST won't help you necessarily. And there's no guarantee that somebody at an event can help you if you run into a problem, but a lot of teams use it. Any event you go to, I'll be there, and I can do anything up here but LabVIEW right now. I'm still working on that. But I'm comfortable with the 3 text-based languages. So let's see. Perfect. All right, so what do you notice about the 2 lines I've got drawn up there? Yeah, what about them? Most of them are green. One of them is red. That's the kind of the thing I'm going to try to use here. If it is red, it's going to carry power. It's going to carry just electricity, energy to make the thing actually work. If it's green, I'm talking about a signal. Now, I'm going to clarify, signals are electricity, but they're very low power electricity. The red is going to be enough electricity to actually make it work. You know, like when you plug in your phone to the wall to get power, but you plug into the computer, you might get power. Same idea. If you plug into a green port, you might get power, but it's not going to be much. If you plug into the red, you're going to get power. So I'm going to point out the things I'm not talking about today first. On the RoboRio, you'll see these I2C, I2C, RS232, and SPI relay. Those are all just names. You know how if you have an Android device, you most likely plug it in using micro USB or USB Type-C, but if you have an Apple device, you use a Lightning port. That's what those are. Those are just different kinds of interfaces. So don't let the names kind of worry you. And like I said, we're not going to be talking about them today that much because they're for more specialized components that we're not talking about today. The goal today is to kind of give you an overview of all the little things that might be helpful to get you started. But the other things we will talk about, we're going to talk about the CAN bus. We're going to talk about those ports up there. We're going to talk about PWM. We're going to talk about RSL, all this other stuff. So if you have a question about something, we'll get there. But one thing to note here, you've got 3 kinds of ports up there at the top. What is that kind of port? Anybody know what that's called? What's that called? That's a USB. What kind of USB? I think these are actually 2.0, but it's USB Type A. This is what you would usually plug into a computer. You can plug devices into these. An example of a device you can plug into the RoboRio right here is a Microsoft HD LifeCam, little web camera you can plug into your RoboRio, and it can send video information to your drivers. Anybody know how big the field is for FRC? It's 54 feet long and 27 feet wide. Camera might be a good thing to have on a robot, and it can plug directly into your RoboRio. Okay, what about this port? That's Ethernet. You plug your radio, which is your wireless communication, into the RoboRio through the Ethernet. You can also plug the RoboRio into your computer. If you are using any computer other than a Windows computer, you probably have to use Ethernet. The reason being that the software that FRC uses for the RoboRio doesn't necessarily support USB over Ethernet for all devices, but if you have an adapter, that'll work too. Just be aware that the Ethernet port is usually going to be used for your radio. And lastly, we have this guy. This is also a USB port. Have you seen this port anywhere else before? It looks kind of like that one, but I don't think it's the same thing. This is a USB port. This is USB Type B. If you've ever owned a printer, this is how you connect to a printer. Same cable and everything. In fact, I had a printer wire at home I just grabbed. Notice that one end is USB Type A, which goes to the computer. One end is USB Type B, which goes to the printer, which gives us USB Type C today, which is why that's C, not anything else. Any questions on what you can see on the RoboRio? Okay. So the next thing is still about the RoboRio. So there's a few terms I'm going to use. Analog signal and digital signal. Some of the components we're going to talk about today use analog. Some of them use digital. So analog is, if you think about older technologies, most older technology is analog. Most newer technology is digital, but that's not going to be true for everything. The thing about analog is it can take any value in a range. So here's a wave that has values between negative 120 and positive 120. Pick a number between negative 120 and positive 120. Right, it'll take 3. What's another one? What else?
I know y'all talk all the time.
4, it'll take 4. What else?
Negative 72.
5, negative 72. What else?
Positive 36.
Positive 36. All right, pick a number between 1 and 10.
3.
10, 3,
5.
5. All right, pick a number between 1 and 3.
2.
1, 2, 3. Pick a number between 1 and 2.
1.
1.5. So that's the key. Analog might also be able to take in between values. So an analog signal has a lot of information in there. You can carry a lot of information in an analog signal. But we've also got digital signal. So digital means, where have you heard the word digital before? What's the key there?
Digital devices.
Digit.
Digit. What's a digit?
There's like a
A
number.
number.
A number like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. Those are your digits. Your fingers are also your digits. So digital signal, unlike an analog signal, remember, analog signal can take any value between its endpoints, more or less. But a digital signal can only take on certain values. What can this one do?
Take 5.
It can take 5 or 0. Now, could I send a number between 5 and 0? I could send it, but would the device understand it? Not the way I mean it to. So pick a number between 0 and 5. I could send 3. The device doesn't know what a 3 is, but it knows what 0 and 5 are. So it said, I got something, and it's going to say this is 0 or this is 5. How does it know which one?
From rounding.
Say again?
Rounding.
Maybe rounding. That's one way. It depends on how you made the device. So whoever made the device said, okay, if you get anything above this value or below this value, that's what it'll be. But if you send something outside those values, it could say, oh, I don't know what this is. I'm going to ignore this. So that's possible too. So one thing to know is that sometimes you will have to convert analog and digital. You could hook up an analog device to a digital converter, which is more common, or you can hook up a digital device to an analog converter, which is much less common. So here the blue curve is analog, the red is digital, and this is the same signal. The blue line is what I send to the device. The red line is what the device understands. So notice here, even though the blue line takes all these different values, the red line can only understand, oh, that's down here, that's all the same. Then it gets to this next step, then the next step, then the next step. So when I say analog or digital, I just mean what kind of information can the device understand? If you're good with this is probably the most technical thing I'm going to get into today. Does this at least kind of make sense on some level? That's all it is. Analog and digital are just 2 ways of communicating, and it's just depending on how much information can you get across at the same time. Analog in one time step can carry more variety of information. Digital has a much more limited range. All right, so some other terms up there. You may see the word CAN anywhere on the RoboRio. Let's see. Up here is CAN. CAN stands for the Control Area Network. Who here drives? Few people? Who's ever been in a car? You have experience with a CAN bus. So Control Area Network, it's a way to communicate between devices. In FRC, we daisy chain our device, and I'll show a picture in a minute what that means. So each component connects to the next one, and each component connects to the one that came before it. Some devices are on the CAN bus, some are not. Not every device on your robot will go on the CAN bus. Smart devices, some of them can go on the CAN bus. Dumb devices can't go on the CAN bus. And it carries data. So here's a picture of a CAN bus. And this is what I mean by daisy chaining. So here is one object, and notice its power, or its signal, goes to the next one, which goes to the next one. And this one's negative goes to the next one, which goes to the next one. That's what daisy chaining is. So the idea is you don't have to connect everything to the RoboRio. So for those coming from FLL, you had motors, you had sensors. What'd you do with them? Where'd they go? What'd they plug into? They plugged into the brick. FRC, your sensors are going to plug into the RoboRio, but they don't have to plug straight into the RoboRio. Who can see an advantage of that? What's nice about that?
You could have more room to use.
Have more room to use. So if you look on the RoboRio, and I'll hold it up, If you had to wire everything to the RoboRio, how many wires is that going to the RoboRio? Right, FLL, how many sensors could you plug into the brick?
4.
That's not too bad. FRC, if you use what's called a swerve drive, you're probably going to use 8 sensors alone just for the wheels. So it's kind of nice when you can start daisy chaining like this. So that's something to be aware of. PWM is another common way to connect devices to the RoboRio. It stands for pulse width modulation. If you look on the RoboRio, I'm going to go back to the picture. All these ports right here are PWM. So remember, when I say these words, I just mean this is a way to connect devices. Don't get too hung up on what the terms actually are. But just so you know how it works, the way that PWM adjusts what information is going to the component, it just changes how long the signal is high or low. So there, the signal's high for half of it. There it's 75, there it's 25%. And so the robot knows what signals it's getting based on how long is it getting the signal, not what is the signal. So this is a way that you can use digital, but get a little more information with one time burst. Now PWM is not CAN, so PWM has to go back to the RoboRio. CAN just goes to the next devices. Any questions on the RoboRio? That's pretty much kind of everything we need to know about the RoboRio right now.
So is this mainly communication devices and power, or is it, or when you had the daisy chain, you just had the positive and negative, so is it just power coming out of the RoboRio, just like turning stuff on and off?
So everything on the CAN bus is signal. So we say high or low for the signal. That's what we're, at least in the context of FRC, our CAN bus is signal. Power comes another way. That's a good question. So everything that goes into in fact, if you look at the RoboRio, everything into the RoboRio except for this is data. The only thing that's into the RoboRio that's power is its input. So the only power from the RoboRio to the RoboRio is the RoboRio getting power. The RoboRio doesn't send power. And so that's a thing where we start to kind of diverge from FL a little bit. Where'd your batteries go in FLL? In the brick. So all your power was there. In FRC, we have a separate device to do power. We have the power distribution panel, and you're almost never going to hear me call that again. It's the PDP. So the PDP distributes power. When I say power, I mean the electricity from the battery to the components that need it. There's 2 kinds of connectors or terminals on the PDP. You've got the Wago, which are these red and black blocks right here, and you've got the Weidmuller, which are these little pegs right here. If you look at the PDP, you can see them when it goes around. So in your home, you probably have either a circuit breaker box or you have a fuse box, right? What's the purpose of that? What's it do?
Directs all the power.
Say again?
Directs all the power.
Directs the power, okay. What else? When you say keeps from shorting out, what do you mean by that? I think I like what you're saying. Yeah. So if you plug something into your house that you're not supposed to, do you want the device to explode? Do you want your house to catch on fire? So guess what the circuit breaker does?
Shuts off once you get an overload.
And how does it do that? It's a circuit breaker, so it breaks the circuit. What's a fuse box do?
It melts the fuse.
It melts the fuse. The fuse burns out, which also breaks the circuit. What's the idea here? Instead of damaging anything, we just break the circuit. If you plug something into a Weidmuller connector, you're going to use, I gotta find it, they're in here somewhere, a circuit breaker to break the circuit. So you may not be able to notice it when it comes around. Try to look at the top. There's a little faint rectangle, and that will pop up if the circuit carries too much current, too much electricity. And over time, it'll lower itself automatically. The Weidmuller connectors, you'll notice up here, have a fuse on either side. And those fuses are what control the Weidmuller circuits. So the PDP can also provide some diagnostics. I'll talk about that in a minute. All right, so I said the RoboRio was a smart device. Based on this picture, do you think the PDP is more of a smart device or more of a dumb device? Why? What makes you think that?
Cause it only carries power, not.
So it doesn't only carry power. It's got one right here, but it's almost entirely power. So I say smart and dumb, I'm talking about their signals. The RoboRio can understand and send a lot of signals. It's a very smart device. Can the PDP understand and send a lot of signals? Can it send any? Why? What can you tell? It's on the CAN bus. And what does the CAN bus carry? Information. So the nice thing with the PDP, if you're on the CAN bus, which you're supposed to be, the PDP can tell you how much voltage is the battery at right now. It can tell you how much current is each circuit pulling right now. It can tell you what is the temperature right now. Why might you want to know those that bits of information? Because it's getting hot. Okay, what's good to know about the battery voltage?
So you know if you need to charge it or not.
Right, and so in FRC you should always charge after every match. You should always have a fresh battery. If you're testing, it'll give you an idea, oh, my robot's not working, why? Oh, the battery's low. Or if you're in the competition, why is this mechanism not working? Oh, we're drawing a lot of power right now. So you can get power, current, voltage, all kinds of things. You can get it for an individual channel, you can get it for everything. So the Wago is where most of your connections are gonna go. If you notice down here, these two Weidmuller connectors, that's where the RoboRio gets power from. And it has a 10 amp fuse there. So if you draw more than 10 amps of current, what's gonna happen to that fuse? Because what's it protecting? You know how much a RoboRio costs?
A lot of money.
How much do you think it costs?
$30,000.
It's about $2,500. Now, as a rookie team, you guys get one for free, and FRC teams can get them for about $435. But it is an expensive piece of technology. To give you an idea, the next most expensive component is the PDP. Guess how much the PDP costs? $200. And you can get them for $200. Let's see. The negative terminal on the PDP goes straight to the battery, but the positive terminal goes to the main circuit breaker. We'll talk about the main circuit breaker in a minute. Like I said, you control, the Wago is controlled with the fuses, or sorry, the circuit breakers. They come in 20 amp, 30 amp, 40 amp. Depending on what component you're using, depends on how much current you need, and it also will affect how big your wires have to be. And then the Weidmuller connectors are protected by fuses. All right, any questions on the PDP or the RoboRio?
What voltage does the batteries?
12 volts. So the PDP and the RoboRio kind of do the job together of what the brick did for FLL. So if you're trying to correlate the two, these two components split off of the brick, and then there's the battery. All right, so some circuits need a little bit more attention. So we have the voltage regulator module. If you are in FRC, this is one other component you need for power. It's used to control more sensitive circuits. So remember I said the PDP could have 20 amp, 30 amp, 40 amp. Anything plugged into the voltage regulator is only going to get 2 amps or 500 milliamps, which is about half an amp. This is used for very sensitive circuits, so things that don't need a lot of power but still need some power. The most common example of this is the radio. Your radio is going to plug into that 12 volt 2 amp every time. And then your 12 volt power comes from the PDP. If you look on the PDP right here, your VRM plugs into 2 of these ports. Smart device or dumb device?
Dumb because it has no information.
There's absolutely no information going to the voltage regulator module. It is a dumb device. It just knows power in, power out. And I do want to point out with the PDP is also that way. It gets power in, it just sends power out. It doesn't know where it's going or how much is going. It just knows send the power. It has no control over how much power it sends. All right, then we got the radio. the radio for FRC. So one of the cool things with FRC over FLL is you get to actually control your robot. And you control it wirelessly. So your robot has this radio on board, and you plug a laptop into the field, and the field communicates with your robot wirelessly. There's a couple ways it can operate. It's an access point, so you can connect directly to your robot at home, and it can act as a bridge, which is how it works on the field. So when you get to competition, you'll have to configure your radio, and they'll have a laptop set up for you to do that, and it'll let you use it at the competition. All right, smart device, dumb device.
It's about a mix.
It looks like a mix, but let's think about it. Power here, is this power going to the radio or from the radio? What do we think? Yeah, because the radio needs power. What's the radio deal with? It deals more with power data. Right, because you're sending information to the radio is sending information where it needs to go, or vice versa. So you plug the radio to the VRM using the barrel connector, and you connect the data to the RoboRio. And notice you're using this, this PoE port. One thing to note, you can bypass that barrel connector by using a power over Ethernet injector cable. Those exist, those are legal. Be careful, because they have been known to cause some problems this past season. I think they're probably more trouble than they're worth, unless they've made any substantial changes. Any questions up until this point? Now, yeah, go ahead.
On the radio, so you said they configure it, so do you have a radio that you work with? Or
Yep.
do you get one?
It's the same radio.
Same radio?
They'll send you a radio in the kit. And the software they give you has a configuration utility, so you can configure it for use at home. Usually just involves setting your team number on it. And when you take it to competition, they'll have a laptop set up. You just bring your radio up, plug it in, and say, I'm at competition. This is the competition I'm at. Here's my team number, and then it's configured to work with the field. Now when you're at home, you don't have to use the radio. You can just plug directly into your robot using a USB cable or an Ethernet cable. At a competition, if you're in your pit area, you have to use tethering. You cannot use wireless communication at the competition unless you're in a designated area, which isn't always guaranteed. But at home, you can use it all you want. Next thing is the robot signal light. The robot signal light is the big red light or the big orange light that tells you about your robot. If your robot's wired up correctly, it's going to give you some useful information. If it's on, the robot's turned on, but the robot is disabled, which means you can't control it right now. If it's blinking, it's on and it's enabled, which means you can use the robot. And it's off, that could mean a few things. What could a robot signal light off mean?
Turned off.
Robot's turned off, what else?
No power.
No power to what? Robot's off, but
Yeah.
maybe,
Wow.
yeah, maybe the light's not getting power. What else could it mean? It could mean a lot of things. Basically, if the robot's turned on and the light's off, you might be in trouble. But if the robot's on and the light's on, you're probably good. All right, everybody knows about the light. Dumb or smart?
Smart.
Yeah, it's smart. It actually knows some things. If you look at where it's plugged in on the RoboRio, it gets its power and its data the same way. So it's kind of a hybrid. Now it doesn't send any information back to the RoboRio, but it's a way to display something the RoboRio knows. Kind of like how my sensor works. That little object I carry in my pocket. This doesn't know what my blood sugar is, but it can tell me what my blood sugar is by talking to my RoboRio. Same kind of idea. All right, battery. Pass this around. Here's a battery. So one thing, and make sure you pick up the battery. One thing to know with FRC, the robot can weigh 120 pounds without the battery. The battery does not count for your weight. It is a 12-volt battery and it carries 18 amp hours. What's that equal? So your robots, this gives you an idea of how much electricity, how much current, how much charge the battery can carry in it. So that'll give you an idea. All right, Smart device, dumb device. The battery is probably the dumbest device on the robot because it literally doesn't know anything. It just sends power. Any questions on the battery? There are only a couple of batteries you're allowed to use, and those will be in the rule book. All right, next component is the main circuit breaker. The main circuit breaker does a couple of things. It protects the overall robot, mostly the PDP, from power fluctuations. It's also your main on-off switch. This is your big red button. Robot's going crazy, what do you do?
Push the big red button.
If it's safe to do so, yes. With FLL, you guys don't have to worry too much about turning the robot off if it's safe. With FRC, these things weigh 120 pounds. It might not be safe to turn the robot off. So turn it off if safe. When you're moving your robot, if you pick it up, move it around, you have to turn it off before you move it. FL, again, not a big deal. They're like this big and they're made of Legos. FRC, these things can cause some damage. Smart device, dumb device. Why is it dumb?
It doesn't really.
No information. Notice the red wire from the PDP goes to one and the red wire from the battery goes to the other. This is just kind of a way to break the circuit when you want to break the circuit. And again, it'll automatically go at 120 amps. If you're drawing 120 amps, something has gone horribly wrong with something. All right, those are basically all the major required components of the robot. If you have all that hooked up, your robot is technically legal. However, it won't be able to do anything necessarily. You could plug a motor directly into the PDP. But what happens when you plug a motor into a battery? What happens if you plug it in backwards? It runs backwards. Because some motors, most motors that are dumb are like that. But when you're driving your robot, what do you want to do sometimes? You always want to be going full speed all the time? Do you want all the wheels going at all the time? No, sometimes you want to control that. So we have motor controllers or speed controllers. And they do exactly what they sound like. A speed controller controls
Speed.
A motor controller controls motor. So remember, the PDP is dumb. How much power does it send to a motor? The answer is all of it. If it says, hey, something's plugged into me, I'm going to send power. It doesn't know how much power to send, so it sends all of it. Motor controllers go in between the PDP and a motor. So one example is the Spark. Spark is a relatively new motor controller. I don't see one in my box, so it's probably somewhere. But anyway, Spark supports PWM connection. So if you're going to plug in a Spark, where does its data go? Somebody said it, I heard it. Where else do you have PWM? So where do you have to plug in a Spark to get data? Does the Spark support CAN bus? I didn't say it did, so it probably doesn't. Spark doesn't support the CAN bus. But one cool thing with the Spark is that you can plug some sensor called a limit switch. What kind of sensor is a limit switch? Sort of. What kind of sensor from FLL would you compare it to, do you think? If you had to guess. Think about it, we'll come to it. It's a touch sensor. You can plug a touch sensor, a limit switch, directly into the Spark. In fact, you can plug two. There's 2 ports there at the top. I think I've got, yeah. So power goes to the Spark from the PDP, and power goes to the motor from the Spark. Now here's where the Spark is useful. All the cool stuff happens in here. So notice the RoboRio is sending a signal, right? The RoboRio says, hey, well let's go through it. Where's the radio at? So the radio gets a signal from the driver's station. The radio says, I gotta send this to the RoboRio. Where's the RoboRio at? RoboRio says, oh, I got a signal from the driver's station. Oh, this motor needs to go this fast. RoboRio sends a signal, hey Spark, this motor needs to go this fast. So the Spark says, okay, I know I'm getting all this power from the PDP, but I'm only gonna let some of this power go to the motor. And what if it needs no power? What's it gonna send?
Nothing.
Maybe not nothing, but it'll send the no speed signal, or the no speed of power. There's a range of power that's okay for that. And then the limit switch can say, if you get hit with the limit switch, stop. Or if you don't get hit, stop, depending on how you have it wired up. So one of the things that we've seen more with FRC lately is being able to plug some sensors directly into motor controllers. Right now, the Spark supports limit switches. Any questions on the Spark? Yep.
So making sure it controls how much power goes into a motor.
Yep. And that's what controls the speed of the motor. And so with FLL, your motors had the motor controller built in, I think. Either the motor controller is built into the motor or the motor controller is built into the brick. I can't remember which one. I think it's probably the motor though. All right. Now these are the ones I recommend. These are probably the best you can get. The Spark runs about probably $40. The Talon SRX runs about $90, and the next one I'm going to show you runs about $50. The Talon is, from my experience, by far the best deal to get. What's one reason that I probably like the Talon SRX based on what you see up here? It's got CAN, which means you don't have to wire it back to the RoboRio, just daisy chain it. But what's another cool thing about this one, based on what I have up there?
It's the direct input from sensors.
You can plug a sensor directly into it if it's the right kind of sensor. So here's how I'm gonna pass it around. Now the cool thing is the CAN wires, you can also wire up to be PWM. So you don't like CAN, you want PWM? Hey, this can do it too. But you can only use the direct input from sensors in CAN mode. Smart device, dumb device? Smart, why? Sending data from the RoboRio from the CAN bus.
To the sensor.
And it can get sensor data directly. So remember, the RoboRio only has so many ports on it, right? If you can plug a sensor directly into the motor controller, you have one less port on the RoboRio. Now you have to have a special sensor for that, and I don't have any with me, but that is an option. One thing to know about motor controllers, they also support a brake and coast mode, which means if I'm not giving it any power, what should it do? So here's what I mean. If you're driving your robot full speed, and all of a sudden you let go, what happens? It depends. If you're in brake mode, motors stop. If you're in coast mode, they roll to a stop. Which one's better? That's exactly right. It depends on the situation, because your motor controllers aren't just going on your wheels. Remember in FL, you had your mechanisms that you attach to your robot. Are those motor powered? Sometimes you want those to come to a rest. Sometimes you want them to just stop where they're at. So if you look on the Talon, there's a little square right below the sensor, and you can just push that in and it'll tell you if it's in brake or coast mode.
So the Spark can only plug in the limit sensor, and then this can plug up most sensors?
I wouldn't necessarily say most, but it has a lot wider range you can use. The Talon SRX is made by, or at least sold by Across the Road Electronics, and they've got a selection of the sensors that they support, and the user manual will tell you what kind of sensors it supports too. But again, and that only works if you're on the campus. If you're on PWM, you can't use the sensor port. But that sensor port is why it costs $90. That's where your extra $40 or $50 goes. Now, if you're not worried about the sensors, the Victor SPX is just as good. It's $50, but it doesn't have the sensor port. But what's nice about it? It can also do CAN. Dumb device, smart device. Smart device, we got data. RoboRio CAN bus. Fundamentally, Spark, Talon SRX, Victor SPX. Fundamentally, there is no difference between the three of them. They all do the same job. However, each one of them has different features, and I would recommend you read the documentation on them to find out which ones are better for your applications. Because it's not going to be that every motor controller, it's not going to be the true that the Talon SRX is the best one for every single robot and every single part of that robot. You'll want to look at the documentation. All right, that's it. And so that's your last kind of actuator for your robot. Those are the actuators in the control system. Next thing I want to do are sensors, and we've only got a few of these. Let me see where I'm at. I've got about 12 more. Okay. Encoders. Raise your hand if you ever used an encoder. If you did FLL, raise your hand. So in FLL, you had encoders. So encoders measure positions of rotation. In the EV3 software, is there a way for you to tell the robot how many rotations to turn?
Yes.
That's because those motors had encoders built into them. It's not necessarily going to be true that every robot, every motor has encoders built in. In fact, we have to provide our own. This is an encoder going around. There's a few ways you can do it. You can, if you have a digital encoder, which I believe these are digital encoders, you take up 2 I/O channels on the RoboRio. Or if it's analog, it just has 1. So if you look on the RoboRio, there are 10 digital I/O ports. If you're using 1 encoder, how many ports is that?
2.
So if you have 5 encoders, no more encoders, right? However, if you've got the Talon SRX, how many ports have you taken up on the RoboRio? 0. Why? You're using the CAN and it has a sensor port. You don't have to plug the sensor into the RoboRio. You can plug the encoder into the motor controller. So it measures rotations. As the thing to know about it. So why is knowing rotations useful?
So then you know how far you have to go.
Right? So with FLL, when you guys controlled how much the motor spun, could you tell it, what else could you tell it? Number of rotations, angle, number of degrees,
Speed,
direction. So you can do about the same with this, and with a little bit of math, you can actually convert it to feet, inches, meters, whatever. But that's something that's done in the program. Any questions about encoders? Again, what do they measure?
So how, so I know there's like a 30-second autonomous period.
Mhm.
I got where that works there. Do you use it when you're controlling the robot? With the encoder
If you
or
want.
not?
If you want. So the idea with the
What would be a
sensors,
situation where you would use an encoder if you're controlling it?
if you have anything that's going on in the background, like if you want your robot to, if you want to, try to think of turning. If you want to calibrate how you're going to turn, PID. You guys use PID in FLL? If you want to use PID during teleop, you're still going to be using your encoders. It'll control your turn rates, your speeds, things like that, so that you're not jerking around when you're driving.
To help you get the grip control and turn?
Basically, if you're any of these sensors during teleop, just help your drivers be a little more stupid if they want to be. If that's a way to think about it. Your sensors during teleop take burden off of your drivers. Makes it a little bit easier to control. Yeah. So sensors are invaluable. Like you have to have them for autonomous if you want to do anything really. But during teleop, they can help you make tweaks and adjustments pretty quickly.
What is teleop?
Teleop is teleoperated. That's where you're grabbing the controls and
Okay.
yeah. So autonomous is like it was in FLL, no touching, and then teleop is driver. Any other questions? If I use a term y'all don't know what it means, stop me because I know a lot of FRC terms. Limit switches. I've got a couple of these. I'm gonna pass them around together. So limit switches are like what kind of sensor? Touch sensor. They detect collisions if you run into something. These are digital because they're either on or off. There's no in between. And they go directly to the Spark, directly to the Talon SRX. There's two ways you can wire them up, and the two I'm passing around, I've wired up different ways. Normally open or normally closed. That's on here. If you look on the side here, down here there's COM. This is your control, your common. Your black wire goes here, and then your signal wire goes here or here. And it just depends. Do you want the limit switch to be normally open, or do you want the limit switch to be normally closed? So if you're trying to detect, hey, did I run into something? Should that be normally open or normally closed? Let's think about it. If you're trying to say, did I run into something? Do you usually run into something, or are you trying to test a special case? It's a special case. So if you didn't run into something, should the limit switch be open or closed?
Closed.
If you didn't run into something. Open, like a touch sensor. The touch sensor is open unless you touch it. So the limit switch, if you're waiting to see if you ran into something. Now, if you've got an arm that's moving, maybe you want that limit switch to be closed most of the time. So that would be normally closed. It just depends on what it's supposed to be most of the time. And you can wire them all up the same way and just change in code how you're reading it. But there's a way to fix it with hardware, and there's a way to fix it with software. Limit switches are probably your simplest components. Any questions on the limit switches? Okay. This is one of my favorite potentiometers. So a potentiometer can measure an angle of rotation. And it's just a fancy resistor. When you turn the dial, it changes how much resistance there is. So it knows how much the angle of rotation is. I think there are some analog and some digital ones. I'm not sure about that. I assume they're all analog, but and if you have one that's supported, you can do it directly to the Talon SRX. So this is another device you have to detect rotation. Encoders also detect rotation. So the difference being an encoder is going to measure something spinning inside it, whereas the potentiometer is the thing that's getting spun. Encoders are really good if you're looking at the shaft of a drivetrain like that. A potentiometer is good if you're just attaching it to an arm that's moving. For example, there's a lot of different applications. One thing you'll notice, there's a lot of sensors that measure the same thing. It usually just comes down to what can you get and what can you get to fit, and what do you have room for. Any questions about the potentiometer? Gyroscope also measures angle of rotation, but it also measures speed of rotation. Measures along one or multiple axes. If it's multiple axes, normally you're going to use one analog I/O per axis. So x-axis, y-axis, z-axis. Am I spinning this way, this way, this way? One thing to know on the RoboRio, there are some 3-axis gyroscopes that plug directly into this SPI port right here. And that's just what you can, that's one thing you can use that for. Any questions on the gyroscope? So remember, it not only measures rotation, but it can measure the speed of rotation.
So what about a good example of using that versus the other options?
Well, again, with the gyro, you can actually measure how fast you're turning. So with the others, it's a little bit harder. You'd have to measure the rate of, you'd have to measure the change, and then measure the time it took to change, whereas the gyroscope already knows that. So that's probably the big difference there. Yep.
Is there a difference between this gyroscope and the gyroscopes we use for the other one?
Probably, but in terms of how it's made, definitely. In terms of how you connect it, definitely. In terms of what it does, no. You guys ever into the problem of gyroscope drift?
Yes.
These can also drift. So fortunately, there's ways in the code to reset the gyroscope. And you can just say, hey, when the robot turns on, reset the gyroscope. And we'll talk about when that happens in a second. But yeah, good questions about that. I saw some trauma pop up there.
I was wondering if that drifts as much as the Lego gyro. We finally figured out a way to stop that.
It probably drifts less, but because the robots are bigger, you'll probably notice the same issue, even though it's a smaller amount. Any other questions about the gyroscope? These are good. Okay. That's a good one. All right, ultrasonic sensor. Sonic means sound. These are good for measuring distances. I got one of these too. And this one, y'all, this was the hardest one for me to wire up last night. I don't know if it was me or if it was my solder or what. By the way, most of these components, you're gonna have to solder the wire to. Everything I've passed around so far that's got a wire coming out of it, I had to solder up last night. I'll show you some tools later. So it sends out a sound wave comes back, and it knows how far away it is. That's about it.
So is this more accurate than the FLL?
Tough to say, because it's probably tuned better, but again, the field is much bigger.
Yeah.
And there's a bunch of different kinds of these. In fact, the one you're looking at right now, this is one of a few that look almost exactly the same. They're different in terms of what kinds of objects they can detect: big objects, small objects, objects look like people, and also how far, but also what their precision is. So 1 meter, half a meter, a millimeter, things like that. So it's probably going to be comparable. Another thing is you can buy several of these and wire them up together, and they've got guides for how to do that so that they work together to give you an overall better image. So I can't really say if it works better or worse, but it usually works pretty okay.
Is it return faster than the Lego?
It's instant.
Oh.
Yeah, well, I mean, let me read it. It travels at the speed of sound. Well, a little bit, maybe, but it's probably the speed of sound, just a little higher frequency.
Lego doesn't, it seems like it's supposed to, but it doesn't quite register fast.
I've never run into a problem with it giving me data back in time. One thing you'll notice is that the RoboRio is a real-time system. I don't know that the FLL brick is, so overall you might be getting some better returns here. Any other questions on the ultrasonic?
Well, how come you solder your wires and don't use terminals? Is there a reason you don't use?
I don't have terminals.
Gotcha.
Yeah. You could solder in some terminals and then use that. But the sensors, like the limit switches, the potentiometer, the ultrasonic, they don't come with anything in the board. So a good idea would probably be to solder in some terminals and then use plugs. But that's what I had. Accelerometer. So again, another thing to measure rotation. This one measures rotation differently. The accelerometer can detect the angular acceleration, which if you want to talk about it later, we can go into the physics of what angular acceleration looks like. But it measures angular acceleration about an axis, it measures tilt, and you can use these bits of information to calculate some things like distance, speed, displacement, all that good stuff. And it can measure along one or multiple axes. Again, analog channel, usually one per axis. The cool thing with the RoboRio is it's got one built in. Right here in the bottom corner, you see accelerometer. It even tells you which way is X, which way is Y, which way is Z. Here's the problem with this. If you want to use the RoboRio's accelerometer, it needs to be in the dead center of your robot. Why?
Because it has to know how fast all those motors are going.
Not quite.
Measure the angles.
It's location in your axis.
So, locations in your axis. That's more what it is, because if you're spinning, so let's say the robot is spinning and here's the middle axis, but the RoboRio is back here in the corner. Your axis is here, but it thinks your axis is here. Is that going to give you the same result?
No.
Probably not. So there's two ways to fix that. One is do some physics, do the calculation, put the correction in the code, or put the RoboRio in the middle. Now, if you're not using that accelerometer for anything super important, if it's just to give you some idea of what's happening, then that's fine. That's probably the big difference with the accelerometer and the others, is the placement of the accelerometer is extremely important for what information it gives you. But again, it's one of those things that measures angular acceleration. So not how much did you turn, not how fast did you turn, but how fast did your speed change during a turn. which can give you some idea of how fast something's going at the end of its thing, how hard it can hit, things like that. Any questions about the accelerometers?
Have you used one like that?
Yeah, I've used the one on the RoboRio.
So what did you use it for?
We used it during autonomous to measure distances. So if you know the acceleration, you can integrate the over time and get the velocity. Then you can integrate the velocity and get the displacement. So we used it to measure our position. That requires a little bit of calculus. Just two integrals. Actually, Riemann sums. So if you ever take calculus, you want to know what is a Riemann sum and why do I need to know it? That's why. Any other questions? Should be about done. I'm just going to go through these quickly. Pneumatics control module is a special device that controls anything with compressed air. Smart device or dumb device? Smart device. It goes on the CAN bus. The compressor does what to air? Compresses it, right? It supplies air to your pneumatic system. Pressure switch. Make sure that you don't exceed allowable pressure. Solenoid is an electric valve that opens and closes air paths. So if you have a cylinder, it can shoot a bar out and pull it back in. It's an actuator like a motor. It just has two positions, out and in. There's some three position, but we won't get into that. I went through the pneumatics kind of fast, but it's just using compressed air and it all goes through the pneumatic control module. Any questions about pneumatics?
Most of your arms and attachments, are you using pneumatics for those?
It depends. One nice thing with pneumatics is overall, if you, at a certain point, pneumatics become lighter to use than motors. So if you've got, let's say, 3 mechanisms on your robot, pneumatics are probably going to be lighter. And depending on what they have to do, like if it has to go all the way out or all the way in, pneumatics are probably better than a motor. Yeah, that's probably what I would say. Just kind of depends on the application. For example, last year on our robot, we had these big ramps that we had to drop down. Finally figured out that the best way to keep them up was a little pneumatic piston, and then we just had it all the way out, and we said, we want to drop them, pulls it up, they drop. So linch pins, they're really good for linch pins. Anything else? Yep.
What happens when you go over the pressure gauge?
When you go over the pressure, the switch sends a signal, hey, the pressure's too high, stop the compressor. So the compressor turns off. And then when you drop below your maximum pressure, it says, hey, we're too low, turn the compressor back on. It's basically the way to make sure your compressor's not running the whole match, because you do have a valve on the pneumatics that detects if the pressure is too high and lets some air out. But if you're holding steady, it'll turn the compressor off. So, yep.
Where's your power for your compressors? Got to run off that 12-volt battery as well?
Let's see. Yeah, so the compressor gets power from the PCM, and the PCM gets power from the PDP. It's one of those special wide Mueller connectors like the VRM got. So it runs down off that 20 amp fuse.
So everything's got to come off that one 12-volt battery.
Yep. So with the compressor though, we'll say this. You don't have to have a compressor on your robot using pneumatics. You are allowed to charge up your pneumatics before a match and just go out with that. Or you can have an onboard compressor. We usually, if we use pneumatics, we have ours on board, but you don't have to if you want to use pneumatics.
What's your tank with that size?
There's a bunch of little tanks. They're probably about this big. How many we used last year? Like 6, 8?
6 or 8.
It depends on how much air you need. We used our pneumatics to actually raise the ramps, so we needed a lot of air to get those ramps up. But for the little piston, we didn't. You could have done that with probably less than 1 full cylinder. It would have. Any other pneumatics questions? All right, I think this is one of the last things is just how the robot operates, and then we'll be done with this section. We can probably eat. The robot goes through states. The robot's off. When you turn the robot on, it enters what is called robot init. As soon as it finishes robot init, it goes to disabled init. Then it goes into disabled periodic. Then it goes into autonomous init. Then autonomous periodic. Then disabled init. Then disabled periodic. Then teleop init. Then teleop periodic. So basically the process is robot comes on, robot start, then be disabled. Autonomous starts. Do all your autonomous stuff. Autonomous is over, disable the robot. Teleop starts. Do all your teleop stuff, and then the match is over. I'm gonna talk about what the inits and periodics mean in a second, but this is kind of your flow of what happens during a match. Now, if you're practicing and testing out, you're not gonna follow this path necessarily, but the thing to know here is that robot init happens as soon as you turn the robot on. And the reason I point this out, the init methods are code that you can put in the robot to say, hey, do this when this starts. So robot init happens as soon as the robot turns on. So if you want your robot to do something as soon as it turns on, that's what goes there. Now that's usually going to be things like reset the gyroscope would go in robot init. You want that to happen as soon as the robot goes on. The problem is though, you turn the robot on, you start moving your robot around, what's going to happen? The gyroscope's going to mess up, the accelerometers, the encoders, all your sensors are going to go off again. So if you put it in robot init, remember that only happens when you turn the robot on. So how would you fix it? If you turn it on, move it around, put it somewhere else, then what? What do you have to do to fix it?
Reset.
Turn it off, then back on again. Autonomous init happens as soon as auto starts. So anything you want to say, I want my encoder to be this value, I want my motors to be going this fast. You can set that in autonomous init. Teleop starts. I want the arm to be at this position as soon as we start teleop. It goes there. So this is code that you want to happen one time during a match and when it happens. Any questions on that? That's a little bit different than with the FLL coding, I know. But this is all stuff that happens one time, and this tells you when it happens. Then you got the periodic methods. These are things that happen almost constantly. So teleop periodic. If you want to drive your robot, the one line of code that tells your robot how to move, you probably want to put that in teleop periodic because that gets called about every 20 milliseconds. Same thing for autonomous. Anything that you want to happen over and over goes in autonomous periodic or teleop periodic. Any questions about the periodics? So I think this is the last thing I want to talk about. Because of the periodics, loops are dangerous. In general, you don't need to add loops to your programs. So with FL, if you wanted something to happen over and over, you added loops, right? I'm gonna tell you right now, assume you don't need to add that loop. I think in LabVIEW, your periodic function actually is one big loop. With the text-based languages, you can't really see that as well. That loop is fine. Don't add any more. There's two kinds of loops. There's for loops and while loops. For loops are me saying, hey, I got these 5 things. I want to do the same thing to all 5 of them. That's okay. That's going to go through 5 things, then be done. A while loop says, hey, do this, do it again, do it again, do it again. But then you've also got the field saying, hey, do your thing again. Hey, do your thing again. So you've got a loop inside of a loop going over and over and over and over and over and over. Guess what happens? You get stuck. You can't do anything. So my rule of thumb is if the template includes a loop, leave it alone. If it gave you the loop, that's fine. If you're not sure if you need to add a loop, try it without the loop first. Just try that first. And then see if you still need the loop, and then maybe add the loop. My takeaway here is just be careful with loops. Loops are dangerous in FRC. They can get you into trouble.
So would you use them in autonomous?
I wouldn't use them in autonomous either.
Which one?
So here's an example. Let's say that all my encoders gave me, let's say I have 4 encoders, and they all gave me a number back. And I want to take the absolute value of all of them. I can say for each encoder in my 4 encoders, take the absolute value. That loop is okay because there's 4 things in the loop and it's just going to happen to those 4 things. While is where you're going to run into trouble. So you can try to think of the way to say it is loops are okay if they're for loops and you're operating on some data. But a loop where you're saying, hey robot, do this thing, that's probably where you're going to get in trouble more often. So loops are probably okay for data if it's a for loop, but if it's for the robot doing something, it's probably a bad idea. And that is it on the slideshow. That is the control system in a nutshell. After lunch, we're going to actually put this stuff on the robot and see if we can get it hooked up. I've got all the hard parts done, and so it'll be mostly connecting. I'm going to show you guys the tools as we go over it so you get an idea of what you might need. If you have any questions, that's what we're here for today. And I hope you learned a little bit about the control system. So let's, whoever's in charge.